Hello everyone, welcome to my lesson. This is Geometry, Constructions, Correspondence, and Transformations. Alright, first of all, I would like to help us remember what are the 8 mathematical principles that Common Core is pushing for, because these principles are very practical. Let us look at them. So the first one is make sense of problems and preserve in solving them. Second one is reason abstractly and quantitatively. I like to jump to the seventh one that says look for and make use of structures. Similarly, number 8, for example, it says look and express regularity in repeated reasoning. And one of my favorite ones is, for example, number 6, attend to precision. In other words, check your work. These are the 8 mathematical principles that we want our mathematical lessons to have. We want to address them all, but I think it's easier to say than to achieve that. And I would like to my lesson with that in mind. All our mathematical principles may not be taught or implemented or explored one mathematical lesson, but I like the practicality of them. I would like to introduce my lesson by giving the objectives. I am doing geometry high school level, and this lesson is based on the Common Core Standards New York Engage. It is lesson 21 for module 1, topic A, correspondence and transformations. The objectives in these lessons are as follows. Students will practice applying a sequence of rigid motions from one figure into another so that he she, they can demonstrate that these figures are congruent. I would like to also bring into context the fact that this lesson has already students been exposed to rigid motions. This is not an objective, but for example, the rigid motions, the students, they're able to synthesize their knowledge of geometric terms with the use of new tools and simultaneously practice precise use of language and efficient communication when they write down these steps. This basically means students are able to perform these rigid motions and to write proofs, mathematical proofs, showing that mathematical truth in modern proof writing and conventional English mathematical proofs. Just to again bring to context these rigid motions that is referencing here are translation, reflection, rotation, and not pretty sure about the Gödel reflection, but these are the 3 basic ones. Now, what is the rationale behind this lesson? Euclidean geometry in high school is an important piece of knowledge, and it opens and connects the algebraic expressions with geometrical shapes. This, in turn, builds up a basis for more complex modeling of 2 and 3-dimensional shapes. Also, in my rationale, I would like to say the approach I'm taking teaching this lesson is an inquiry-based approach. I believe that this approach is ideal for geometric constructors, whereas students at this point have already been exposed to rigid transformations. There is still room for some curiosity and culturally responsive shapes, as we will see in our next slide. As you can see, this geometrical shape of these multiple geometrical figures, polygons, are just the beginning of what could happen in this geometry class. Now, let us review what Berner and company talked about on their piece Development of Competencies for Teaching Geometry through an Ethnomathematical Approach. Here I quote, is initially perceived geometry ornaments as pictures, develop alternative perceptions of them as figural structures and as objects of geometric inquiry. They are referring in here to students approaching geometry. However, for Werner and company, it is important for students to communicate to these geometrical shapes and for them to analyze these ornaments. For example, here we have this star, but this star also shares a golden ratio, and students in this Israeli public school setup can relate this star to their culture and also see how this important ratio. So instead of them looking at triangles and pentagons and polygons that are ornamental, they can look at the geometry throughout the whole environment. Also, teaching geometry through the ethnomathematical approach, yet new courses can also use these patterns. For example, icons, 3D cultural artifacts, origami, architectural of elements. The learning of these activities can include construction and analysis of physical and computer models. Initially, I mentioned Euclidean geometry as an important mathematical foundation for more advanced modeling, and we will talk more about it in our at the end of this presentation. Now let us look at what Edwards and company come up with cultivating a deductive thinking with angled casing. And I quote, both inductive and deductive reasoning are essential in the discovery of mathematical truth. Thus, students require experiences using both kinds of thinking. Here is an extract figure of this reading, and it is important for Edwards and company that students by themselves start to chase these angles, because when they learn these mathematical concepts, there are three initial steps. Three steps. The first one is an initial deduction. The second one is an inductive step, and the final is the final inductive. Fostering student reflection with an angle chasing, the symbolic of cues embedded in the angle chasing provided students with clues for determining unknown angle measures. In other words, for Edwards and company, proof writing equals mathematical truth. And it is important for students to first be able to experience this angle chasing, and second, be able to write them down in mathematical formal proofs. Now, for our third article, we have Compass Constructions, a vehicle for promoting relational and understanding of higher order thinking skills. This is by Koch, and I quote, a change in approach to a small topic can promote higher order mental activities and provide relationships between topics. Recalling on what we have been learning in our class, there are students with fixed mindset and growth mindset. This is a call for a growth mindset in students and is always keeping um, in the back of our minds as teachers that we have to keep those high expectations. So here teachers may find these extensions of constructions of problems solving are too difficult for students who may have just learned the procedures of angle bisections, construction perpendicular bisectors, and straight line segments. However, it is more complicated constructions which involve higher order thinking skills and provide motivation and the application of these skills. So, in other words, for COD, students develop a growth mindset when they face these higher order mental activities. All right. Now what? After researching the approaches of these three scholars, I'd like to come up with these three conclusions. First of all, literature assumes students' readiness while pacing guides and classroom management make 42 minutes of instructions go so fast. In all of our approaches, students are ready to learn, and if they struggle, we can scaffolding. However, the inquiry-based approach that I'm trying to implement in my lesson or final project may be hindered by the limited amount of time. Second, ethno approaches push us to see the ornaments in our culturally rich architectures. I found that very engaging and I hope to apply that to my mathematical lesson or final project. Also, common core standards are on the practical side. An art class work cross-sectional curriculum could make some geometry class beautiful at work. Just realizing by these ornaments and how can they become and how they are understood as beauty among creation, human creation, it is an important thing to bring to the classroom. As I mentioned earlier, inquiry-based approaches demand students' readiness and group activities. COVID may be an obstacle for me in the current conditions due to the mask wearing and the social distance set up in my classroom. Finally, I believe that non-Euclidean geometry, yes, that geometry that deals with parallel lines that will intersect, is not mentioned in a conventional geometry construction. However, the curvature of lines is a concept that helps the creativity aspect of the construction. Going back to those constructions, the ethnocultural, the mathematical truth statements through proof writings, all of that, I would say, it will end up in important aspects of constructions like precision, like creativity. I believe that in my classroom, I must motivate or create or incentivize this creativity because this is not a fixed topic. All right, with that, I will end that my presentation. Thank you so much.